in all its glory. All right, so some of the things that you're going to be expected to do on your Regents exam is going to involve the manipulation of a polynomial. First of all, what is a polynomial? I mean, you guys have been answering this question many, many times throughout the course of the year. I just haven't used the word. When I said, guys, how many terms are there, right? You're adding terms, you're counting terms. Guys, those combination of terms is a polynomial, right? So a combination of terms. And what could those, oh, by the way, how are you combining those terms? By adding and subtracting, right? And furthermore, guys, right, the polynomial can be terms that have variables, don't have variables, have coefficients, not have coefficients, have exponents, not have exponents, right? So here I have 4 different choices, one of which is not a polynomial, 3 of which are. There is only one that looks a little bit different, and it's only because of one small thing. Which one of these do we think is not a polynomial? Choice 1, 2, 3, or 4? Just 3, yeah. I mean, just on sort of like common sense, what doesn't fit, right? So what's weird about choice 3? It has exponents that are what? Negative and fractions, right? So those are not allowed. This is not a polynomial. All right, the other ones are. And so you're noticing, guys, that one of the things that must be a definition for a polynomial is that the powers have to be positive and not fractions, right? Positive and not fractions. So in the definition, they're all raised to non-negative integers, right? Integers meaning not fractions. All right, so here's the next phrase, identity. Guys, identity means that one side of an equation is the same as the other side of the equation. Now, when I say the same, it means they have the same value. They may not actually look like the same polynomial. So for example, if I said x squared minus y squared, well, based on last unit and previous units, wouldn't you guys agree that that's a difference of perfect squares? What makes it a difference of perfect squares? How many terms? 2. What am I doing to them? Subtracting. And all the powers are even, so they must be perfect. So this is one of those problems that I could factor into what? X plus y and x minus y, like that, right? So when I do that, I typically don't write it this way, do I? What do I typically do? I typically write this underneath it and be like, yeah, I factored it. Cool, right? Well, guys, when you write it underneath it, what are you implying? You're implying that this has the same value as that, aren't you? Well, when I write it this way, I write it as an identity. So this is an identity. And what has to be within an identity? What has to be there? What did I add to this that you typically wouldn't have there? The equal sign. Yeah. In other words, the left side has the same value as the right side, right? It's an identity. Now, one way that you can test an identity is by taking 2 unique values, plugging them in, and seeing if you get the same result on both sides of the equation. Now, in this case, you're using the values of 10 and 3, right? What would be bad values to test within an identity? What would be values that you probably don't want to use? 0 and what's another value you probably don't want to use to test an identity? Ariel? 1, yeah. 0, 1, and -1, guys, are usually values that you don't want to test within an identity. And the only reason that you wouldn't want to test those, now I'm saying, okay, let me back up for 1 second. When you're doing a polynomial identity, it really wouldn't matter if you use 0, 1, and -1. But if you were testing an identity that might involve rational functions or things like that, you probably don't want to use those values, okay? For this purpose, you could get away with it, but as a general rule of thumb, don't use it. Cool? All right, so we're going to test 10 and 3, right? So I'm going to plug those values in. 10 squared minus 3 squared is equal to 10 plus 3 times 10 minus 3. So what do we get here? We get 10 squared, which is 100, minus 3 squared, which is 9. What's 100 minus 9? 91. Equals 10 plus 3 is 13 times 7. And guess what? 13 times 7 equals 91. And so, yes, this is an identity. Now, here's the problem, right? This is not considered a I'm going to use an ugly word for the geo students. This is not a mathematical proof. Why is this not a mathematical proof? Because a mathematical proof has to encompass all possible cases of x and y, not just the case of 10 and 3. So if this is an identity, then algebraically, I should be able to get one side of the equation to look exactly the same as the other, right? So if this is an identity, then I should be able to get both sides to look exactly the same. Well, what could I do on the right-hand side of this? What could I play? Tic-tac-toe, right? So if I played tic-tac-toe, x times x, x squared. What's x times y? X, xy, right? Yeah. What's x times negative y? Negative xy. And what's negative y times y? Negative y squared. Ooh, I wrote the wrong thing. Hang on. What's supposed to go here? X, negative x what? Negative xy. Okay. So if I look at the stuff that's in blue now, right? I'm supposed to combine all those terms, right? And what happens when I combine those terms? Well, the left-hand side, this is what I'm trying to match up, right? And those blue terms give me this. And what's cool about this, what happens to the two middle terms? They cancel out, and so the left-hand side winds up matching the right-hand side. And so, yes, this is an identity. And this is considered an algebraic proof, right? In the sense of the term, because now it works for every possible value of x and y, doesn't it? Right? Is that cool? Nothing crazy there, right? So what are some things that I could do with this? Now, I'm going to tell you right now, guys, everything I'm going to show you right now, you'll never, ever, ever, ever use. You'll never see it on a test, okay? Well, you're going to see concepts that we're going to use this concept to build on something else. Let's just put it that way, okay? But what I'm going to show you per se right now, you won't need to do, but we will use it, okay? If I wanted to do this, and this is what ancient mathematicians did years and years ago, they had stuff like this. I want 50 squared minus 49 squared. Well, there's got to be a way to do this that can use an identity to evaluate without using a calculator. So if I think about what we just proved that this equals this, right? Well, if I write this underneath it, 50 squared minus 49 squared, that looks exactly like this, doesn't it? It's written in the exact same format. Except, what have I given the value of x? And what have I given the value of y? 49. Well, according to the identity, this equals this. Well, can I take these values and plug them in over here? And if I did, what happens? Well, I get 50 plus 49 times 50 minus 49. What's 50 plus 49? 99. What's 50 minus 49? 1. So this is equal to 99. So 50 squared minus 49 squared, 99. Didn't have to do anything with the calculator. It's called number theory, actually, guys. This is number theory. It's looking at how numbers interact. Use this identity only to simplify and then evaluate this product. So now I want to know, what's 51 times 49? What is 51 times 49? Okay. Well, we're going to use this identity. And here's what we're going to do. How did I get 50? Is there, again, I want to just sort of use some common sense for a minute. What's kind of special about 51 and 49? How might I get those two numbers? What could I do to get those two numbers? Add or subtract 1 from 50, right? 50 plus 1, 51. 50 minus 1 is 49. Well, 50 plus 1 is 51. 50 minus 1 is 49. And what am I doing with these two things? Ariel? I'm multiplying them. So I'm sort of doing the problem that we did before backwards now, aren't I? So what am I calling x in this case? 50. What am I calling y? 1. Well, that's the same as 50 squared minus 1 squared. What's 50 squared? What's 5 times 5? 25. And how many zeros do I need to add? 50 times 50, so 2 zeros. So it's 2,500. Minus 1, which is 24.99. Again, number theory, right? All right, so here's another identity, right? A plus B squared. All right, it says I want to prove that this is equal to this. Now I'm going to say this, and I know when the test comes around, somebody's going to write it down, and I'm going to look at them, look at their paper and sneer. Okay? Yeah, exactly. That's Jamie's sneer. Do it like this. Guys, you can't distribute exponents, right? So a plus b with the square outside, the square does not get distributed. What does it mean you need to do? Times it by itself. A plus b times a plus b. So that means I get to play tic-tac-toe again, right? And if all goes well, when I play tic-tac-toe, I'll get the same thing on the other side, right? So a squared, ab, and b squared gives me the identity. So we're champions. Cool. So there's something else that we need to do. What might this identity be useful for? Well, I want to evaluate 35 squared. What is 35 times 35? Well, what could I do? I could sit here and I could do it out algebraically, right? Or not algebraically, but by hand, by longhand. I could use a calculator. I get all that. But here's what the identity is saying. It's saying 35 squared. Give me two numbers that you know the result of the square of that add up to be 35. Pick numbers that are easy to square. What do I use? What do we know what 30 squared is? Come on, you're supposed to be my energetic group. You guys are disappointing me right now. 900, thank you. Because 3 times 3 is 9 with 2 additional zeros, right? And do we know what 5 squared is? Of course we do, right? So couldn't I rewrite this as 30, as 30 plus 5 squared? So now what can I do? Well, I've given myself a value for A and a value for B. So A equals 30 and B equals 5. And what am I going to do? I'm going to take these values and plug it into this and evaluate this to get the result. 30 squared plus 2 times 30 times 5 plus 5 squared. Somebody said 30 squared is 900. Plus, what's 2 times 30? 60. What's 60 times 5? 300. And then 5 squared is 25. And put this all together and you get 1225. So kind of fun to me, because I'm a dorky math teacher. All right, so as I said, guys, this concept really isn't a concept that you're going to need to do, but it is going to bring us into an idea that you may need to do. And that's something like this. A right triangle is shown below. Those of you that took geometry last year know why I put that there. Okay. Show that these will be the sides of a right triangle as long as x is greater than 1. If this is a right triangle, then what should these values work within? What should I be able to do with these values? Use them within the Pythagorean theorem, right? Square the two legs, add them together, and it should be equal to the third side squared, right? So, by the way, when I use the Pythagorean theorem, I know that I'm using A, B, and C, right? What is always the side that is C? The longest side. So yeah, this would be your C value. And then it doesn't really matter which values I call those. I could flip-flop them or label them this way, okay? And then what am I going to do? I'm going to take 2x and I'm going to square it. And I'm going to add it to x squared plus minus 1 squared and see if it's equal to this squared, right? Well, if it is, then this is a right triangle. If it's not, then it's not a right triangle. So let's do this. 2x squared. What is 2x squared? What's 2x times 2x? 4x squared. plus. Okay, what do I need to do here? Distribute the square? No. Do x squared minus 1 times x squared minus 1. Equals, what am I going to do here? X squared plus 1 times squared plus 1, which means I actually have to play tic-tac-toe twice. All right. I like having colors here, guys. I know that I'm going to wind up taking these 4 things and combining it with that, right? So I just want to make sure that I do that. Everybody agree with that? All right. X squared times x squared. What is that? X to the 4th, right? Good. Then I have negative x squared and negative x squared and positive 1. So what do I wind up getting? Well, x to the 4th can't be combined with anything, can it? So that's kind of on its own. And then I have 4x squared minus x squared minus x squared. What's that going to give me? 2x squared plus the 1. Okay, so does that equal what we get on the other side? Well, on the other side, I have an x to the 4th, and I have an x squared, and I have an x squared, and I have a 1. It would. You're saying right here? Okay, good. I'm so glad you said that. This is minus 2x squared, but I had to combine it with, right? So it's 4x squared minus the 2x squared. Got it? All this together? And yes, they actually match. So this is proven as an identity. Guys, what does that mean in the context of this problem? What does that mean in the context of this problem? Yeah, you can plug any numbers into it and it can work. In other words, it's a definite, 100%, no question about it, right? Triangle, right? Because what did we do? We took the sides and we plugged them into the Pythagorean theorem to see if we got an identity, to see if the left side and the right side matched. So this is a right triangle. And again, what did we not use here? We didn't use numbers to do it, did we? Right? Typically, we show something as a right triangle by using numbers, right? Here, we used algebraic expressions, okay? Guys, cross out part P here. We're not going to do this one. All right, last little bit here, guys. Again, prove this identity, right? So what am I looking to do here? I have a plus b cubed, and I want to see if it matches that thing on the right. How am I going to do that? How do I cube something? How do I cube something? How do I do 4 cubed? What do I do? 4 times 4 times 4. Okay, how do you do 4 times 4 times 4? How do you do that? Who can explain it to me? How do you do 3 times 3 times 3? How do you do 5 times 5 times? How do you do it? How do you do 2 times 3 times 4? Can you multiply three things at the same time? No. So how do you multiply three things? Multiply the first two, get a product, and then take that product and multiply by the third. Yeah. So when I do a plus b cubed, what am I going to do? I'm going to take the first two items, get that result, and then multiply that result by the third item. Yeah, so I'm going to play tic-tac-toe and then take that result and multiply it by the third item. So the result is a squared plus how many ABs? So a squared plus 2AB plus b squared. And I'm going to multiply that by the third item, right? So if you think about it like this, guys, one, watch this. I'm going to color code this. This is going to be cool. 2, 3. So what did I do here, guys? I took this and this, got the result, and I'm multiplying it by the third item now, right? That's it. Okay. So now what do I have to do over here? Play tic-tac-toe, except the, I don't know, cheater's edition or something. Or genius edition. So what do I get here? Well, I get a squared times a, which is a cubed. A times 2ab is 2a squared b. Any of those like terms? Any of those get combined? Those and those, right? So I have an a cubed. I have 3. Oh boy, that's a 3. And so look at that. It works. It's an identity. It's kind of nice, guys, when you get one of these because it sort of like gives you the answer. So, where might something like this be useful? Well, guys, anybody in the room know what 11 cubed is? I don't. But I bet you we could do that. So what have I done here? I've made what value 10? The a value, and I've made b. And so according to this identity, if I cube the a and add it to 3 times the a squared times the b, and 3 times the a b squared, and add the b cubed. Yes, guys, I understand that that's more complicated than doing 11 times 11 times 11, okay? But you have to understand something for a minute here. I'm using really small numbers of 11 cubed, right? Now I want you to go back to the ancient times, okay? The ancient times where mathematicians were trying to figure out the calendar, and mathematicians were trying to figure out what a day is, right? Guys, it's not by chance that we have 24 hours a day and we have 365.25 days in a year, right? Mathematicians from years and years ago did calculations and figured all of that out, okay? And some of the math they had to do involved big exponents. So if I asked you guys to calculate not 11 cubed, but 11 to the 40th power, let's say, having a formula to do that might be more useful than doing 11 times 11 times 11 times, right? Get the idea? All right. So there may not be, it may not seem, Shayla, like a really significant like find right here, but if we think about it in the context of bigger math, it might be useful, okay? 10 cubed, 10 times 10 is 100, times 10 is 1,000, plus 300, plus 30, plus 1. And hang on one second, guys. I better, thank you. Yeah, they are on my desk. So put those all together, and what do you get? 1,331. 1,331. We had 1,331. Okay. Boom. All right, example 6, guys, I am not going to do with you guys right now. I'm going to do this at the beginning of the next class. We're going to use it as an introduction to the next piece we're going to do.